All right, welcome back. We are INFR3110. That's Game Engine Design Implementation in the Fall 2020 semester, and it's week 3, part 2 of our broadcast. Even though it says part 1, we're actually part 2. In part 1, what we did is we talked about your assignment and GDW requirements for your project. So I've kind of went through a lot of detail there. So if you missed that, please look at your video part 1 for week 3. All right, so what did we do last week? So last week we talked about software engineering and UML. I went into quite a bit of detail about UML. Hopefully you guys downloaded Star UML because chances are on your midterm, which is coming up in a few short weeks. Is it a few short weeks? Wait, 2 weeks. It's 2 weeks, right? Because it's like we're sitting at week 3 and in week 5 you're going to have your midterm, if I'm not wrong, right? Week 5. So in a couple weeks, we're going to do your midterm, and you're going to need to know how to do a UML diagram, at least, or a flowchart, or pseudocode, or one of these 3 for your midterm. Notice that we're repeating some of the same requirements so that you know how to do them. I'm not going to try and give you random requirements out of the blue that we haven't talked about for your midterm. But here's what's going to happen, like we talked about in the first video. Your midterm is going to be practical, and it's going to cover the things that we have already learned about as an example in the first weeks. Okay, that's what it's going to cover. It's going to be individualized. You're going to get it on the Monday. It's going to be over by the Friday. And by the Wednesday, when you learn about DLLs, you'll be getting together with Nicholas, and he'll be showing you or guiding you through with a template. And there'll be different feature sets that everyone will have to do. Okay, and I'll explain that as we get closer. All right, so that is what we did last week. That's why it's important. And we also talked about game engines. We kind of did a tour or an exploration of different commercial game engines, both open source and proprietary. Last week at a very high level, we talked about them and why, what we do with game engines, why game engines, and all that kind of stuff. So that was last week. So what are we doing this week? This week, I talked about your assignment 1 details. We talked about your semester project. We're also going to be talking about game engine architecture at kind of a lower level, as well as what does Unity look like from an architecture perspective. We'll talk about that as well. Okay, so that's what we're doing. There will be no individual assignment today as a bonus, although I will try and include them as much as I can as we go. All right, so when we talk architecture, what is that? Well, it refers to the fundamental structures of software system, really, at the end of the day. That's what we're talking about, the structures of a software system. And when we think about what a runtime engine architecture is, and we're going to repeat this in a second, is it consists of a tool suite and a runtime component, right? A tool suite and a runtime component. The runtime piece, what it is it's made up of several layers, okay? And that's what this slide says here. So there's different layers. The upper layers depend on the lower layer, so there is a dependency. And when the lower layer depends on the higher layer, this is bad because it creates almost like this circular dependency. We don't want that. So that's why they create, most people, when they do their architecture design, they start off at the bottom layer and they say, we don't have any circular dependencies. And this dependency can cause something like an undesirable coupling, which is what we want to avoid. All right. And this is especially true for this crazy large-scale system, which is what an engine is. It's a massive system of interconnected parts, and we're going to go through each of the components together, slowly, and I'm going to explain them. It starts like this. We have some kind of input and some kind of output. I mean, really, that's what any kind of game is. I have inputs for the game, human interface device, and my game responds to to me as a user. That's what it comes down to, right? So what I want the engine to do is I want to read inputs. I want to update the cameras. I'm going to update the game world. I'm going to update the user interface, update the AI. It's all going to happen according to my input. I'm going to influence the world. In fact, if we look at games user research, which you guys should be hitting next year, if I'm not wrong. Maybe I'm thinking next year, unless they reorganize the courses. One thing they talk about is in play heuristics, they talk about how a good kind of design for all games that you make, it should be that the character your game is character centric, right? Whatever your avatar or character or your player is affecting the game world, right? So that's really what the game engine architecture supports, right? It's all about, your interaction with the game, right? And this is where it's a blurry line between, am I making a game here or am I making a game engine? And I'm going back to that. When we start off making a game engine from scratch, we want to think about the game that it's going to support. That's the most important piece, right? Because the game is what you're making this game engine for in the first place. So let's start really simple again. Let's not forget about the user, because the user is the input. He's the input system, if you will. He's going to connect to the game, and there's going to be several subsystems that are going to provide feedback for the user. And that includes things like audio, visual, haptic, and olfactory, potentially in the future, feedback, which means maybe you're going to have a smellorama in the future. Right now, there's no smellorama necessarily, but maybe in the future it's going to be a thing where, it's more realistic. You're immersed in the game. You've got some kind of VR element, not just spatial audio, but spatial smells. I don't know, right? But it's gonna come that way where as game engines evolve, you're going to be immersed in the game more and more, and that's what game engines are supposed to do for the user. So again, really at the end of the day, what we want to be able to do is from the architecture, we want to kind of connect different piece parts to provide not just input, but provide some feedback to the user. So it kind of looks like this, right? We have some kind of input. The input causes us to have some kind of rendering that comes back to the user. Notice there's like a double arrow here from input. The screen renders something. Input affects the AI. The user's input affects the game loop. And through the game loop, we get things like audio and a user interface update, game logic. And that comes from an underlying framework of subsystems, for example, that allow me to draw or get input or have sound, whether it's spatial audio or impulse sounds, utilities, anything like that. That happens at the bottom level, right? So this supports all of this interaction that happens, and it starts with the user. Okay? So again, pretty straightforward stuff so far. And so we have these messaging kind of components. So some kind of game logic. We have a messaging bus, a lot of times almost like a queue. And what happens is in the messaging bus, we send across messages from the user through logic into the input system, the renderer, the scene management system, the audio system or the audio manager, and it goes back into the back-end framework where it connects with, at the lower end, our drawable objects, our input system, our sound system, and so on, all these subsystems. I know it sounds like one thing kind of connects with the other, but really, at the end of the day, this approach allows us to multi-thread. And why? Because, well, here's actually a really, in my opinion, this is something that when we're making a game engine, we would want to do, first of all and foremost, we want to separate each of the systems so that I can apply different threads, if I need to several different systems. Like, for example, maybe I'm going to have my update loop run different on a different thread than my renderer, right? And why? Because I can allocate resources separately to those two things. I don't want to tie my update loop to my renderer. That can, create some other problems in the future. And we're going to talk about that when we hit the game loop in a future lesson. So the idea here is the architecture allows us to decouple our components from the back-end framework. And it also allows us to separate our concerns. So I can have different people, different engine programmers work on different components, different parts of the subsystem. So when we're working with a large system like this, you can work in a larger team. So let's think about the engine again. And again, this is going to start off with layers. So we can think about our game engine. It's a bunch of interconnected parts. Think about them as a black box right now. And we're going to build it up in layers. So the very first layer is the hardware layer. Okay? So this is where we connect to things like a PC hardware, the Xbox, PS4, PS5 in the future now, the Switch. And there's different kinds of platforms that we're connected to typically. Some kind of Windows, Linux, or Mac OS platform. A mobile platform nowadays is the iPhone, the iPad, Android smartphones and tablets, and game consoles that we talked about before. So that is the hardware layer, the first layer. And that's the lowest level. And that means that, and I always think about the OSI model when I think about the hardware layer. When I think about the hardware layer, I'm also thinking about how does the hardware interconnect with the software. Okay? And we're going to do that through device drivers. So I'm going to have, for example, maybe you were lucky enough in this round to buy the latest RTX 3090 graphics card. Anyone have a chance to buy the new RTX cards? Did you beat the bots and buy them? How about a hands of X's for no and check marks for yes in the participants panel? I'll guarantee you, if I see a check mark, I'm going to be really impressed, right? Because I don't know anyone. First of all, maybe you didn't even try and get them, and B, chances are you got there's no way the bots probably got them all. Yeah, I see a bunch of X's, which is what I thought. And I am also seeing stuff like, I'm waiting for Big Navi. I don't know. I'm not sure if I'm convinced that Big Navi is going to do better than the RTX 3080. And I also have a comment here that says, I don't think anybody is going to drop $1,500 as a student. Yeah, some people might do it if they're hardware enthusiasts. You never know. But yeah, I hear what you're saying. It's a lot of money. And if anyone says they're lying, or they have it, they're lying. I agree with that because I couldn't get one, and I was waiting for that to come out. I remember I am a hardware enthusiast, and I want to get an RTX 3080 at least, if not a 3090. All right, but anyways, the hardware connects to our software with a group of drivers, and this is kind of a lower level software component. And think about that each card has something called firmware, and we should have learned about that in computer architecture when you did it. The firmware itself speaks to the software and creates an API or some kind of application programming interface or a programming interface for each of the devices. So I want to connect to a GPU. I'm going to create a set of drivers, and the set of drivers for that particular GPU is going to allow me with software to activate different components and its performance. Whether I want to send information or messaging back and forth to that component, or whether I want to store data in that component, for example, in the GPU as some kind of compute shader, whatever I want to do, the driver is going to be our information bus, if you will, to transfer between the software and the hardware. Okay? So that is your device driver. So beyond your device driver then, on the next layer, is the operating system. Your operating system connects to your device drivers, and usually that's running all the time. Example of that would be Windows. Windows is constantly running, right? Your host operating system, if we're running Windows, or if you're running a console, consoles have their own host operating system. Usually they're running a Linux kernel of some kind in the background, or some kind of customized operating system for that particular console. Older consoles obviously had a smaller version of an operating system. And I don't want you to think of an operating system that we have today for Windows. Example, when you access something like a VR device, the VR device also has an operating system, but the operating system is like a customized version of an Android phone, right? So think about an Android operating system, and that's what you're seeing for VR, for let's say something like a Quest, right? So the operating system talks to the drivers talk to the hardware. Okay, and the drivers are written in some kind of lower level language, could be assembly, and it's probably flashed onto the device through firmware. All right, so and then what we want to think about is that when I think about the operating system, let's think about desktop operating system for a second. Then most operating systems these days, they use a time sliced approach that they call it multitasking or multi-threading. And what that allows us to do is, for multitasking, it switches between tasks. So I'm working on my operating system, and then I also communicate with my with this program that's running at the same time. It's not really happening at the same time. If I have a single core CPU, what's really happening is I'm trading processes. I'm going with one process and then very quickly going to the next process and the next process and the next process. And so it looks like I'm multitasking, but really what I'm doing is I'm task switching, and I'm doing it so quickly that it looks like I'm handling everything at once. However, if I have a multi-threaded system, and if I have a CPU with multiple cores, I can handle multiple processes and multiple tasks, and each of those tasks can have subtasks. So this is where, again, most modern architecture has the ability. If you buy a regular computer today, most likely it's going to have a couple cores, like a dual core at the minimum is what I've seen out there. It's very rare, unless you're running an older laptop, or if you're running a phone or something like that, that you're going to have a single core. Now that might change as we move and we kind of migrate from, let's say, especially the predominant architecture out there, which is something like an x86 architecture that Intel is using or AMD is using on the current platforms right now. Once we move away from x86 and we go towards from a CISC-based architecture to a RISC-based architecture that we're moving towards, with Apple actually pioneering that with the ARM processors that are going to be coming out at the end of the year, and maybe that's going to influence the our entire hardware ecosystem, where maybe our game systems in the future are also going to be ARM-based. Maybe we won't need to do multi-core systems as much, because a RISC-based processor is more efficient in some ways, or deals with operations differently than a CISC-based processor. RISC versus CISC, and we're using a CISC-based, CISC, CISC-based, right? So again, it really depends. But right now, most of us right now in the course probably have at least a dual-core processor that we have in our little machines. And some of us have more cores. If you're running something with like an AMD, if you're lucky enough to have a Threadripper or something like that, you can have up to 64 cores, which is pretty awesome, especially when it comes to video creation and 3D graphics and so on. From a console perspective, they do have like a mini operating system. And the earlier consoles, their operating system was more like a library layer. It wasn't really a full-blown operating system that we're used to, for example, Windows, Linux, or Mac. It was kind of a customized or proprietary operating system that was just allowed things like a user interface to pop up to allow you to start and stop a game. That's it, and in the earliest versions. Later on, especially now with, let's say, the latest Xbox and PS4 units, their operating system is more robust because they can afford it. They have more memory, and they're a lot closer to a PC now than ever. And in the next iteration, we're entering the new modern Xbox and PS systems. They're going to be so much closer to a PC. In fact, there's a lot of predictions that Xbox and PCs, they're going to merge in terms of their version of Windows. Windows are going to be able to run on both at some point in the future. There's some speculation around that, or some version of Windows 10 that's going to run on the Xbox. We'll see if that comes to light. I mean, they already support keyboard and mice, so let's see if that goes. Then let's talk about consoles a little bit more continued. A lot of times what they do is, they use an interrupt that allows you to stop the game, pause the game, put it aside. Very similar to what we do now with mobile operating systems. When I have an application that I send to the background, so I can answer a call. Right? I get a call on my phone. I'm playing a game, let's say at a bus stop or something, and then I'm going to put it away. My app that I'm working on gets put away, and then I see my phone call coming in, right? And so it interrupts what I'm doing. Nowadays, with modern mobile operating systems, for example, iOS 14 on the Apple ecosystem, it actually doesn't put your app away into the background. It does some kind of overlay that basically says, hey, by the way, there's a phone call coming in. Do you feel like answering it, or are you going to keep watching The Boys on Prime? As an example. It's up to you. So that's happening more and more, where we have almost like a near multitasking capability even on our phones. So consoles before, they were kind of like a very skimmed down version of an operating system, almost a very low level kind of a way of switching tasks. and nowadays they're closer to kind of a desktop operating system. So that was the OS layer. Now we're moving into the next layer, which is third-party SDKs and middleware. So what are those, right? Well, you have things like, I want to be able to support different subsystems, and this is where everything starts. This is the first layer, if you will, of our game engine. The first very, very bottom layer of the game engine. So far we haven't even talked about game engine. We've talked about hardware and software and drivers and all that kind of stuff, but now we're talking about the actual game engine itself. So you have to choose what kind of third-party SDKs and middleware that your game engine is going to start to employ. And what I mean by that is, are you going to use DirectX for your rendering engine? Is it going to be OpenGL or Vulkan? What are you going to use for that? That is your third-party middleware or SDK that you're going to tap into, or some kind of API, an application programming interface. And what about your physics system? Are you going to be using, Havoc, PhysX, or something else, right? Are you going to use some other kind of third-party library to help you with serialization and deserialization? Are you going to save and load things using Boost? It's a massive library. By the way, I did it one time. It was purely by accident. One of my TAs at the time said, "Hey, we want you to open up I was making a particle systems editor with my partner, and then we were trying to put together in C++ a little menu, and I'm thinking, let's use Boost. Why not? And of course, Boost was massive, and it made our app bloat like massive, because Boost is a huge system that you can get through NuGet on Visual Studio. But it was awesome. I mean, it just did a lot of stuff, but maybe way more than I wanted. Way more than I wanted. It was kind of like an overkill for what it gave you. You can also, of course, use the standard template library or some kind of port of the standard template library, or a cut down version, maybe your own version. You might want to make a customized version of the STL, because maybe the STL itself is not efficient enough for you from a C++ perspective, where you want to cut it down and make it more efficient. KinApps for AI, or maybe you're going to choose some kind of animation engine. The Granny 3D animation engine is, again, something that's out there. Havoc animation, another one, or maybe even a customized version. Something like Euphoria. Yeah, exactly. I agree with you, Anthony. Insert the video there. And so on. So those are all your third-party SDKs. You're going to choose a group of them that's going to interface with the OS. You're going to bundle them together, right? And those are the libraries. Either you're going to make them on your own. So let's say, for example, I want to use WinAPI instead of for my windowing system. I'm making my own game engine, or I want to base on an SDL, or I want to use GLFW. Whatever I'm going to use for my OpenGL, layer, right? I'm going to connect that, right, to OpenGL, or let's say DirectX or something else. So those are the two, third-party SDKs I'm going to use. They're not the game engine, but they're components of the game engine. Let's think about these. We're going to need data structures and algorithms. Now, whether I make them on my own, or whether I use ones that have been created for me, that are already out there. For example, the standard template library, or if I'm going to use something like GLM, which, I mean, let's face it, a lot of us use GLM when we're programming OpenGL or Vulkan. That's what's happening right now, right? Why? Do I really want to reinvent the wheel when it comes to making a vector or a matrix? No, GLM is out there and it's a pretty good library, right? But sometimes a library like GLM is also big. It's massive. It takes up a big memory footprint, and I want to do my own. I want to make my own vector 2 class, or my own vector 3 class, and so on, because I can make it probably smaller, that's what I'm thinking, than GLM. But be wary of that, because remember, those libraries have been optimized with templating and a bunch of other technologies out there to make them as efficient as possible, and they've been tested to death. Your idea, it's great for learning, but it might be something where you're recreating the wheel as well. So that's, we're talking about third-party SDKs. Let's keep talking about graphics. We can choose, kind of a direction we want to go in. Do we want to use OpenGL? Do I want to use Vulkan? Do I want to use DirectX? Let me tell you, when I did advanced graphics with Dr. Hogue to do Vulkan, wow, what a massive library. I had to write 800 lines of code to draw a triangle. That's insane, right? And so maybe we're going to use an engine out there that already does some of that stuff for us, or some kind of third-party plugin where maybe someone's already, created a part of an engine that I can use. I can plug that part in for myself instead of me writing all that code on my own. Now, if you're making a game engine, you may want to make your own wrappers for Vulkan, so that way you can connect and, draw your triangles, do your rendering and all that kind of stuff, right? But it's pretty heavy duty. One thing to note is the most popular, kind of rendering for Xbox is DirectX, still, even though Vulkan has more performance gains, right? So, OpenGL, and when you talked, one time we went to conferences. We met with kind of representatives from AMD, and we were showing them our game at one of these conventions, and they said, "Hey, it's really great they're using OpenGL, but OpenGL is dead, eh?" This is AMD. They said, "We'd rather have you kind of using Vulkan," and we're like, "Yeah, Vulkan, but it's 1,000 lines just to get a triangle going, and yeah, we're not going to do that." So so that's why a lot of people use DirectX, because it's very well documented. It's older technology. Vulkan is kind of bleeding edge, and Vulkan takes advantage of your GPU a lot more efficiently, and it handles the graphics pipeline much differently than OpenGL. So again, you have to decide what you're going to use there. The next one is, okay, what physics engine am I going to plug in? Okay, as an example. Am I going to plug in Havok, right, which is very popular? Microsoft uses Havok for almost everything. PhysX, if I'm making a 2D game engine, am I going to use Box 2D or Bullet or Canon.js? If I'm making something on JavaScript, there's a lot of different piece parts that I want to plug in, and I have to decide that part. What is going to be my physics engine? Or, and this is crazy, do I want to write my own? Do I want to make a whole other project, or have a whole set of other people, who are going to make their own physics engine, right? And again, when we say physics engine, we're talking about rigid body dynamics and collision detection, because really that's what we use it for, from a game development perspective. We don't really make physics, okay? There's limitations on what we can do. Although some of the beautiful engines that are out there right now, especially the commercial ones, they do a lot. They've done things like fluid dynamics, all kinds of soft body physics and interactions. They do a lot of biomechanical things, amazing things that you can do. And again, these are people that's their forte, right? So again, physics engine, game engine, two different things. And a lot of times, game engines use existing, established, tested physics engines. A good example of that is both Unity and Unreal. Unity and Unreal, they don't reinvent the wheel. They actually use established physics engines. So Havok and PhysX. The next one is character animation systems. So again, we just mentioned them, Granny 3D, Havok animation. So Havok doesn't just do physics, but they also do animation. Endorphin and Euphoria are another two different sets of animation systems to help us do character animation in 3D. Could we make our own? Absolutely, we can make our own, and many people do. But again, if I'm going to make, IK work for my particular game, right? Do I want to code IK from scratch, or do I want to use a system that already has IK support, right? Inverse kinematics. Do I want a system that already has FBX loading support, or do I want to write my own FBX loader? Like, these are all things you need to consider as it's going to make your job to create your game engine bigger, right? And there's someone who's already done it. All you need to do is plug it in. It's still going to be your game engine. It's just going to use different components from these third-party SDKs that have been established. The next layer is the platform independence layer. Okay, so this is where we want to be able to create systems that can run on any platform. So, for example, things like I want to be able to detect the platform that I'm on. Am I on a Mac or a PC? Am I on an Xbox or a PS5? What am I on? Right? Am I on a Switch? Right? So that's platform detection is what they do. They're also connecting with the file system. So something that's platform dependent, they're connecting to it. There's going to be some kind of wrapper that connects with the file system, depending on which file system it is. So again, we want to make our engine as platform independent as possible. Now, sometimes that's not always the case. For example, some engines just don't work with Linux, right? They're not made for Linux. They're made for PC, and Mac is an afterthought, right? I mean, let's face it, how many games are made specifically for Mac? In fact, if anything, we translate a game from PC to Mac with some kind of middle step, some kind of translation engine. And a lot of times we use Java for that, okay? So, so many times, although we might say platform independent layer, we don't care about the platform. We don't care about the kind of network transport layer that we're connecting to or whatever. That layer a lot of times is more platform dependent than we'd like, all right? And it's just the way it is, because a lot of times we make a game, and most games are made for PC. Nowadays, there's also a thought to making it compatible with PlayStation and Xbox. So again, you can see there's a bunch of wrappers that we create in this layer. Above the platform independence layer, or the ability for us to connect with the operating system and the actual platform itself, we have a bunch of core systems. And these are examples of management systems, math libraries like GLM, custom data structures and algorithms. You can see there's a bunch here. Things like I might have some custom profiling, parsers, CSV, XML kind of parsers, loaders, different things, serializers, deserializers, that kind of thing. And that kind of floats on top of my platform's independence layer. All right. So all the managers, they start here. I want to allocate memory. I'm going to tie my my memory manager, into this core system somehow. Again, it's all kind of climbs from one layer to the next. And some of these layers can be super small, especially if you're making a little independent game engine. They don't have to be as massive as this looks right now, and they may not include all these components. On top of that, we have a bunch of resource managers. All right. So for example, I manage 3D models. I have a texture manager. I might have a material manager, a font manager. I might manage things like skeleton resources, collision manager, physics manager, some kind of game world tile map kind of loader manager. And there could be many other ones. An AI manager that deals with the brain or the agents, all AI agents in the game. Okay, all that kind of stuff. So we have a bunch of managers. Now, I'll tell you right now, when I code any kind of game engine from scratch, whether it's 2D or 3D, some of the first things I code are some kind of singleton-based managers. So for example, a texture manager, if I was going to do a 2D game engine, it'd be one of the first things that I create, because it creates a cache. I can reuse a lot of the textures. And you're going to see that kind of, one of the reasons why we want to make a game engine is so we can reuse. We can reuse code, we can reuse textures, we can reuse memory, right? And be efficient at it every frame. So that's your resource management layer. On top of that, now there's a bunch of layers that are on the same level, if you will. The first one is this low-level renderer layer. And this low-level renderer layer, it's part of the rendering engine. And I'll have to tell you that the rendering engine itself, because graphics are so important for a game engine, is the largest component, if you will, of the entire thing. It's the largest component. Why? It handles everything from drawing basic geometry, primitives, and all that kind of stuff. So the whole pipeline that many of us have forgotten from intermediate graphics and all that kind of stuff, this layer here, this low-level renderer, starts to handle all that kind of stuff. It's the device interface between DirectX and OpenGL. It handles things like textures. It handles lighting. It handles so many different things here. And that's why the rendering engine is so powerful. And let's remember the graphics pipeline here. I'm not trying to make it so that you get nightmares looking at this. I know some of you had some interesting experiences with intermediate graphics. Every time I think, I was trying to think about myself as a graphics programmer, and I would never call myself that, because it's a whole other layer of programming prowess, if you will, right? It takes a special person to be a graphics programmer, and it's a lot of detail. But take a look at the pipeline, and this pipeline here that we should all know about is something that is handled by that low-level rendering layer. Kennedy says she passed, and that's all she wants to remember, and it hurts my brain too, for sure, when I think about for graphics, for sure. So let's stay in that rendering engine. So we thought about the pipeline for a second, and now we're still in that rendering area, but we can also do things like our graphic device interface, which basically enumerates the available graphic devices, initializes them, and sets up rendering surfaces. Our buffers, as a good example is what they do. Okay, so that's what the graphic device interface layer inside, that's a sublayer or subcomponent of the low-level renderer. That's what it does. Okay, we're going to stay in here for a bit. You're going to see several slides here just on the rendering engine, because that's how big it is. The other thing is this idea of a scene graph or culling. One of the things I do when I build a 2D game engine, one of the first things I do is I start thinking about how I'm going to create a scene graph. How can I add things to the scene? What things are going to be included in the scene and what things are going to be culled. All right, and this a lot of times has to do with what my camera is able to see. So let's think about this. If you think about one of the techniques we use when it comes to light and shadow, and is depth testing, right? The ability for us to actually, detect layers, as an example, inside of our scene. And there's going to be some layers that are or some objects that are occluded, right? Or they're going to be hidden behind other objects, and so we use something called occlusion culling to not draw these things, right? So this is all, again, part of this rendering engine layer, and specifically when it comes to the scene graph and culling. Culling also happens, again, with our frustum. So we have our near plane and our far plane, like we've learned before in intermediate graphics, and anything between those two planes, if you will, is something that's going to be drawn or rendered in our scene. Anything outside of that frustum, which looks like almost like a truncated cone, are the things that are going to be not drawn. They're still in our game world. We still have them in memory, but they're not in our rendering loop. Okay, we're not drawing them every frame. Okay, so that is something that we can do with our rendering low-level renderer. The rendering engine also takes care of visual effects. So things like particle systems, decal systems, for example, like let's say bullet holes, that kind of thing. I spelled color correction wrong, of course, when I was doing this slide. Yay, Tom. Light mapping, dynamic shadows, HDR, full screen, anti-aliasing, and a bunch of other stuff that is handled here in the rendering engine. So it does all those post-processing effects. So that we got from our intermediate graphics, things like depth of field and all that kind of stuff. That's all handled with shaders, the use of shaders, of course, through the rendering engine. Okay. Let's continue. Then we also have our front end. A lot of times we have a front end to the game, to the rendering engine that includes things like how do I render things in screen space. If I want a kind of a screen space renderer to render a HUD or overlay or some kind of menu that I want to show that appears to be 2D, but really, remember, everything that we do in game making is an illusion in many ways, right? We want to show that there's an overlay on the screen, but we're really rendering in 3D. All the 3D engines out there, they show 2D stuff, but it's really on a single plane, right? And you're going to see that with Unity. Unity is actually a 3D game engine, but we can render 2D elements on the same plane using something like the painter's algorithm, where we have layers of textures one on top of the other. So this is considered our front end, and the ability for our game engine to handle layers like that and to produce 2D artifacts, 2D elements and so on, is part of the front end, quote unquote, of our rendering engine. Okay. Next to the low-level renderer, at the same level, is the profiling and debugging system. Okay, and a lot of times what we want to do is, it's not enough just to make a game engine and let it go. We also want to know how it's performing. And one of the things we're going to be doing this semester here in this course is doing a little bit of profiling. I'm going to get you guys to build a memory profiler, right? So, or at least in your game, your group project part 2, I'm going to ask you to meter your memory usage in Unity, which means you're going to capture kind of like your inefficient, kind of version of your code. You're going to use some memory optimization or optimization design patterns. Example would be the object pooling. And then what you're going to show is the effect of that design pattern on the operation of your game. Okay, so that's the idea behind it. We're going to talk about how to do memory profiling. But memory profiling in general, memory profiling and performance profiling and debugging is definitely it's part of the workflow when we make our game engine, right? Because we want to be able to have statistics pop up that show, guess what? We're running at 60 frames per second, but we really want to run at 120 frames per second. What's slowing us down? Where is the memory being allocated? As an example, is there a memory leak? What's causing the memory leak? And we can kind of, go down that rabbit hole iteration after iteration to improve our game engine so it has better performance and that there is no memory leak and it has a smaller chance of crashing our system, which can happen because remember, we're building an application at the application level, which could effectively reboot our computer sometimes if we're not careful. I'm not sure if any of you, I'm going to put my hand up. Have any of you had this situation happen? You've downloaded a Steam game, you're playing it, and all of a sudden your whole computer reboots. It's happened to me, right? Because of the way, check mark if this ever happened to you. If your computer's ever like just rebooted randomly, you're playing a game and you're like, that game, it makes me reboot my computer once in a while when I played it a long time. If you say no, then you're lucky. But for me, it's happened many times over the course I've been playing games. Thank you for that feedback. Your game used 7 gigabytes of memory? Anthony, what are you doing? What are you building? A missile silo game? Like, what the heck, right? Rocket science. So there's some really cool general purpose profiling and debugging tools you can tap into. Intel's VTune, IBM's Quantify and Purify and Ensure++. And there's also custom profiling that you make on your own. You want to a profile display, some kind of stats to the file, like a logging system, memory monitoring, and a bunch of other things that you can make on your own. And a lot of times we do make custom profiling systems. Okay, we talked about the physics engine, and remember what we want to incorporate the physics engine into a physics system. So yeah, we have a physics engine, but we want to wrap the physics engine into something that's usable, an API that our programmers can make use of, is what I'm saying, right? So if I want to make ragdoll physics work, well, I got to enable that for my game engine. Even though it's there, the API is there from using Havoc, I need to wrap that API into something that my programmers can use, right? My gameplay programmers. And I might have to do that in a higher level script. So this collisions in physics subsystem is something that I need that ties into the the physics game engine or the physics engine that I've incorporated or plugged in here, right? And again, we want to think about physics as kinematics of rigid bodies and forces, dynamics that occur that cause motion. That's as far as we want to go when it comes to most of our games. And one thing I also have to say is collisions. Collision detection is kind of a central part of any game, right? Because if you can't detect collision, especially when it comes to certain elements of our game, that's going to take away from our gameplay. And a good example of that is if you haven't been able to map dynamic collision between bullets. Let's say my bullet hits your bullet. Do you care? Maybe not in 3D, but in 2D, yeah, it might look weird, or whatever. Or how about there's two moving bodies, they're both moving quickly, and I have a very small body that I want to detect collisions on. I might have a tunneling effect. My bullet might go right through, because from each frame that I'm trying to detect collisions, if I do very simple collision detection with bounding areas, right, or a bounding hierarchy, as an example, then I might run into problems. And one of the things we build in here, whether we're using a physics engine or not, is how do we do collision detection? Do we use quad trees or oct trees, voxel oct trees? What do we use for detecting our collisions? Do we split the game world into voxels, the entire game world, right? And do we detect collisions based on some kind of influence. When we do things like broad phase to narrow phase collision detection, how do we make that efficient? Do we have a dip in performance when objects come closer, when we start collision detecting as things come closer and closer, or do we have some kind of consistency of play, right? How do we do that? And these are all things that you have to consider when you're creating a physics system. Our physics, there's a comment from Roderick. Our game last year had deletion problems at first, so it ended up using up all space on the laptop. Yeah, it's happened to me too, Roderick. You're not the only one. Let's continue. Animation. So most commercial game engines that you're gonna tie into have their own animation systems, subsystems. So we talked about tying into something like the Havoc animation system, or maybe in Unity's case they have something called Mechanim, and Mechanim your animation system might include something like a state machine, where you want to basically move your characters from one state to another state. So for example, I might have the walk state, where I'm showing a walk cycle as an example, and then I'm going to move from the walk cycle into a run cycle. How do I transition? Do I have some kind of morph target? Do I use blending? What kind of animation systems do I have in place, as an example, to make it so that it looks buttery smooth as opposed to choppy, right? I don't want that. Does my animation system also include IK, like we mentioned before, or am I going to have slidey feet when I for my 3D characters? What is it going to look like, right? So all these are considerations as we tie the animation system that someone's created into our game engine. Let's continue. We also have the need for some kind of input. So we call these human interface devices, and we have a whole lecture devoted to different kinds of human interface devices and feedback for players. Feedback is such a huge design consideration when it comes to game design. Like, for example, how am I going to get feedback? Does it really make sense? Am I going to get rumble from the gamepad that I'm using as an example? Or do I want to use the accelerometer now in the new PS5 game controllers? I don't know, right? How can I tie all this in to provide a better experience for my player, or is it just going to be the traditional mouse and keyboard way? And I'll tell you, I was playing Flight Simulator several weeks ago when it first came out, and I was trying to do it with mouse and keyboard, and I was like, yeah, there's got to be a better way. There's got to be a better way, right? But be honest, I couldn't think of a better way. There's so many switches that you have to turn on and off in a plane. So maybe the mouse and keyboard was the best interface, or maybe I needed a real cockpit in VR. I can't wait for Flight Simulator to come up with a really great VR interface where you're actually in the plane and you can see the switches and you can turn them on, as opposed to, wait, I've got to use my arrow keys to move around the cockpit so I can look at the left side of my window or the right side of my window. It was really annoying, actually. If I had some kind of thrust stick, some kind of flight stick, right, it made it easier. Like I remember back in the day when we were doing, flight simulators, we had flight sticks and some kind of thruster. It made it more realistic. It gave us a sense of immersion. And whether you're piloting a plane or in a fighter jet, as an example, it gave you that feeling that it was more realistic. So that's what the human interface devices do. But how do we hook them in so that we can have multiple people playing at the same time on the same system, or multiple inputs, or in the future maybe there's going to be other kinds of things that we're using. And a good example of that, for rhythm games, maybe I'm going to have some kind of dance pad or something else, another kind of interface, not just your standard game controller or game wheel. So these are all things that are considerations, again, when it comes to your game engine. But I want to mention that this input is something that you want to make so that when you're making your game engine, it's the most common inputs that your game engine is going to handle. For example, if you're never going to do a rhythm game with that particular game engine, maybe you're not going to listen for music input. You're not going to analyze. You're not going to have a machine learning interface that listens to the music to provide messages for your game. Or maybe you're not going to connect to a dance pad because you're never going to make that kind of game. audio is often, unfortunately, overlooked, and we've talked about this if you've ever done Professor Capralis Bill's class on audio. He'll talk to you about the sound guy. There's only one sound guy or girl nowadays, and it's almost like sound somehow, for whatever reason, is still not as important for some people when they make their game engines. But some people are getting it, and they're making it so that sound is such a huge feedback component for players, right? We don't want to forget this piece. So we want to include nowadays things like spatial audio. We want to use dynamic sound effects and music so that when there's a conflict that happens in our game, we can use dynamic sound to make the player feel more engaged or change their emotional state, right? Which is what sound allows us to do. Without a good sound system and the proper number of channels in order for you to handle this thing, and again, Fmod is one of the systems we can use. We can plug Fmod right into Unity as well. We're going to have trouble. Are you going to make your own sound manager? And I know that there's some people in our year that did. That is also something you can do for GDW project. You want to make your own sound manager. But if you don't think about this kind of stuff, it's going to impact your game. Obligatory game sound club plug. No, it's not just for that. We need it. It's super important. And we can't forget about it. There's a need for somebody who is a composer. There's a need for somebody who is who's going to create the right sounds, the appropriate sounds for your game. Guys, don't forget about this for your GDW projects. Multiplayer. It's huge. There's more social gaming these days than anything else we do, and if your game engine doesn't support multiplayer, then you're going to be at a disadvantage, because maybe you're going to have to plug into some kind of multiplayer interface in the future, and you're going to have to do a little bit of rewriting. Okay, let me take that back. A lot of rewriting, reworking of your game. So if you're thinking about multiplayer for your game, build it into your game engine from day one, right? Here's a challenge. Sometimes what we want to do is we want to turn multiplayer on or off. Maybe we like to make single player games, and we're probably never going to do multiplayer. Again, I think the common wisdom is build in something or plug in a third-party component that allows you to connect and use an API to do multiplayer. One of the challenges we have right now is that Unity, our game engine of choice right now for this semester, still their UNet system, their networking system, is still deprecated, and they're in the process of changing it up and making a brand new networking system that they've been working on for the last couple of years. I'm still looking forward to seeing it. For now, you can use Photon. That's something that's available to you through the Unity Asset Store if you're going to think about doing multiplayer. I have a question from Anthony. What about networking as a requirement for us? Should we start networking from the start? We tried doing that, and we were making Manos returns. I'll tell you that we thought about doing networking from the very beginning, and I can tell you that you've got a lot going on this semester, and you're going to be learning about over the next little while. Next semester, you're going to be doing your networking, distributed networking course next semester, and I think I'm not going to say wait. I'm going to say start building subsystems to plug in and plug out your networking components. So what I mean by that is maybe what you want to think about is start planning doing couch co-op today, right? And then replace your couch co-op components, your messaging on the back end, with some kind of networking system. I think it might be smarter, and it might reduce your load, your scope for this semester, because you're going to have a pretty big scope this semester. And I would recommend leaving networking to next semester. Would I think about building systems around it or a wrapper? Absolutely, and you may want to talk about some upper level students around how they did it, but I highly recommend you wait. Photon Bolt, that's really cool, Matthew. That means you're thinking about, like, you're talking about visual networking. Is that what you did? I'm curious about that. And maybe you want to share that with maybe a link that you want to share with the class, and I'll post it up on Canvas if there's a plugin. Because if it's something that's fairly straightforward, I support it. If it's something that is going to be very involved and it's going to increase your scope, and the scope is going to be like a massive bazooka, please don't do that. It's a more FPS-focused version of Photon. Yeah. Okay, that's fine. If it's something you're going to do with Photon is the way to go anyway, because like I said, Unity's unit that you made a little FPS. I wouldn't recommend Bolt for GDW since it's closely couples with everything. I agree. Bolt in general is great for prototyping, I think. So if I was going to give, if you didn't know anything about coding and you wanted to make a subsystem, as an example, or if you're learning how to code, Bolt might be good. You know what I'm saying? But if you're a programmer, I think Bolt will just slow you down, in my opinion. Right? Now, there's some things that can be done with Bolt, that, for example, you may not know how to do with code, but if you're a programmer, then Bolt, for me, Bolt or even visual programming is a negative. However, I have to also say this, when we were doing Unreal this semester, just previous to, in the summer, my group was using Unreal. We tried doing the low-level programming with C++, and I'll tell you that we could do things twice as fast with visual programming. So, it really depends on the game engine, I think is the answer. If we're using Unity, I still think the best way to use Unity is the scripting API, right? That's just, how I would probably do it. Not to say that Bolt isn't cool, and the things that you can do with it aren't awesome for what you get. The time you put in is you get a lot out of it. All right. So again, going back to multiplayer, without a good multiplayer system, especially nowadays, or if you don't think about multiplayer in your games, then I think you're going to get bitten later on. I think you should provision for it in the future, but not do it now, unless you already have experience doing it. If you have someone on your team who's already done networking with Photon, all the power to you. Do it now, if you can afford to. But if it's something that's going to add load and it's going to prevent you from hitting your milestones, I would say leave it till next semester. Cool. So you made a small project for you. So Matthew's is saying he made a small project so he can test out how it all works. Paraphrasing Matthew, sorry. The next layer is the gameplay foundation. So we're building up, into the next layer. Notice that there's the renderer, and next to the renderer still we have this other layer which allows us to do things like, that allows us to use our gameplay mechanics to connect to our engine. Okay, so things like any kind of action the player takes, all of our gameplay systems are kind of scripted together, and they connect to things like the event management system, your real-time simulations, AI as an example, world loading and streaming, and a bunch of other subsystems that are part of gameplay foundations layer. So let's think about game worlds and object models. So things like the contents of the world, your static background, dynamic rigid bodies, your PC and NPC items, lights, cameras, all that kind of stuff are part of gameplay foundations that actually enable you to do mechanics. So a good example of that is, frequently I have these people who are students who want to do things like, I want to make a 3D platformer, Tom, and I want to use some kind of grappling hook. Okay, grappling hook platformer. What kind of grappling hook are you going to make, is my question. Are you going to make a grappling hook that pulls your character towards the point where the grappling hook hits? Or are you going to make the grappling hook swing the character to the next platform? And they're like, swing? Yeah, no, we're not thinking about swinging. We're thinking about just pulling the character towards the point. And the reason for this is because, from a mechanics perspective, doing that plus adding physics might be really challenging. But that whole writing of code is inside this gameplay foundations layer. All right, so that is a little bit more. The event system is super important. And a lot of times we use the observer pattern, which we're going to learn about this semester right here in the event system. So messaging can be at different levels. Sometimes I want to click on a button, I want to hover my mouse over something, and I want to get a response. I'm listening for different kinds of interactions from the user or feedback that's coming from the user's actions, and then I'm going to handle those actions through some kind of event handler. So I have an event listener for different kinds of elements in my game, whether they're 3D models or UI elements, or it's a trigger that I've gone over or something else. And then I have an event handler that handles that triggered event. I trigger the event to happen, and then I handle the results of that event, right? This triggering and handling uses the idea behind it is the design pattern is the observer pattern, which we're going to talk about, which is I have something that's observable. Example, a button. I'm looking at the button. I'm observing it, right? And then I have the observer, right? And the observer allows subscribers to subscribe to the event. The observer is the event listener. The event listener is looking at the observable, which is my button, as an example, right? And the event listener, right, when I trigger the button, it notifies all of its subscribers, everything that's subscribed to that event. I'm listening for the button click event. As soon as I click on the button, I'm going to notify every piece of logic that's subscribed to me. I'm going to notify them. I'm going to push notify them that guess what? The button's been pushed. Another example of the observer pattern, which we're going to talk about, is achievements, right? You have some kind of messaging. You've achieved a certain level. You've got some XP. You've finished a quest, whatever you're going to do. You can use the observer pattern to notify the system, the achievement management system, that something's happened, that your player has achieved some kind of level of gone from one level to the next or whatever, right? So this is all part of gameplay foundations. Then there's game-specific subsystems. Again, another layer. Now this layer is the next layer on top of gameplay, all right? So now we have things like player mechanics, game-specific rendering, game cameras, and AI. And we've talked about a couple things. You guys should have already learned in your algorithms course about things like flocking and things like steering behaviors. Yeah? Can you give me a check mark if you learned steering behaviors in your algorithms course? You should have. I'll tell you that part of AI that Dr. Hogue taught us when I was going through that course with everyone else, thank you guys for that feedback, was probably one of the most interesting components of learning about AI. It's the simplest kind of stuff, and when you do AI in fourth year, one of the things they talk about is like, well, that's not really AI. That steering behavior stuff, no, that's not really AI. In that pathfinding stuff that you did, that's not really AI, right? AI is more behavior based. It's more goals and decision making, goal oriented behavior, right? Things like reinforcement learning, which is something we learn about in fourth year, which is awesome. How does the system learn? How does an AI know where I'm going to be after traversing the game world? That kind of thing. All that AI subsystems and everything else, the brain of each of your AI agents, those are the things you build into this specific subsystem. And you can see there's other things here, power-ups, vehicles, puzzles. We're going further up the chain, right, where we're much higher up than we were earlier. So that is really the top layer of our game engine. This is where we have everything exposed so that the game would be playable. All right, things like you see here, the player follow camera, the debug fly-through camera, and a bunch of other little systems here that are able to be used to create things like weapons, power-ups, vehicles, puzzles, etc. Those are all the outputs of all these other subsystems. Okay, so that is your game engine architecture. And I know it took a long time when we went through the entire thing. Will you be tested on this is always the question that I always get. And you may have, I'm trying to make it modular, but you may have some questions in your final exam around this. But remember, your final exam, if it's up to me, will be open book. You'll have access to this stuff. You're going to have to talk intelligently about game engine subsystems a little bit. All right, at least know enough that you know approximately where everything is. If I ask you something like, are the drivers higher or lower than, game-specific subsystem, in your mind you should say the drivers are pretty low. Drivers are like almost at the level of the hardware, right? So at least if you know that kind of stuff, general ideas about how your game engine is kind of laid out, I think that's important to know and know where to look and how to answer your questions. Let's look at a couple of systems that have been created or game engines out there. And this one comes from the Game Engine Black Book for Wolfenstein 3D. This is one of the earliest game engine architectures that we saw. So you can see here that you have a memory manager and a cache manager and a page manager. You see a bunch of managers here. And then there's the Wolf 3D engine. And the Wolf 3D engine ties into all these managers on the outside. Look how weirdly organized this is. And this is kind of one of the earliest things that they thought about, right? So you got to think about how this moved from here until we went and did the Doom engine, which is this one. Here's the Doom source code. This is like second iteration Wolfenstein engine. And you can see how all of a sudden how differently organized it is compared to the first one. Why? We learned how to start putting things in some kind of order, right? We started thinking about things in subsystems. The video system, the audio system, the RAM system, the network system, and so on. And it started formulating right from there. So this is the kind of, almost like an evolution of how we got to this game engine architecture that I showed you today. How about Unity? What the heck does it do, right? Well, the basic level that you're going to be using in the Unity game engine is it's all component driven. Please don't think of it as entity component system. It's not quite like that. We have entities, but it's not quite an ECS, not in the normal operation mode. Can you make it an ECS? Absolutely, with the burst compiler and everything else. But it's a totally different model, if you will. And Kyle says, were some nodes extending outside of the box? They were insignificant. I'm not sure that they were insignificant. It's just that it was less organized. So here's the game engine architecture for Unity. So you have a scene at the very high level, if you will. Inside the scene, you have a bunch of game objects. That's how it works. Each game object contains components. So it's component driven, like we said before. And each component, every game object must have a transform component. That is just the way Unity works, right? No matter what it is, whether it's a camera component, or camera game object, or whether it's an empty game object, every one of them has a transform component. And that includes position, rotation, and scale. That's your transform. Then you have a bunch of optional components. A renderer, a rigid body, and other mono-behavior scripts that you can attach, or user-defined components that you attach onto your game object. So really what you have is a component list. That's what it is. If I was going to reprogram or something like this, if I was going to try and do something that's very Unity-like, I may make a component list, a component vector in C++, let's say. I would make a component superclass, and then I might have each of these components derive from or inherit from the component superclass, right? And then I would add them into the component list, whether it's a linked list or just a vector, all right? And then what I can do is I can enumerate all of these components, right? So I can say, I want the transform component, I want the renderer, I want the rigid body. You can also make, instead of using a vector, you can use something like a dictionary if you're going to make an engine like that. And the dictionary would have key value pairs where the key is the name of the component and the value is the reference to that component. Okay. At the end of the day, this is how it works. And you have systems, so cameras and physics, data, configuration, animations and textures, and behaviors, which are your game mechanics and your scripted events. So this is kind of how Unity is laid out. When you use Unity, when you learn about Unity, if you haven't learned about it already, especially as Nick gets you more and more into it starting next week, you're going to see that this is how Unity is laid out. Unity uses something called a scripting API, all right? And I want to talk about really that at a very, very high level right now. And so why do we even need a scripting API? Why can't we just write things in like low-level C++, where, by the way, Unity is written in C++, right, on the back end. It uses C++. But it also uses something called high-performance C#. High-performance C# enables Unity programmers, or the game engine developers to give up their code, as an example, to somebody who's not a low-level programmer, right? So why is that? Because if I was to give my engine code, if I was to open up my engine code to people that maybe are not as good, or maybe they're not game engine programmers. Game engine programming is a skill of its own, like graphics programming, right? I might make my game engine unstable, right? So in order for me to do that, whether it's an indie studio or a AAA studio, I offer up a script front end for users who are perhaps not coding at the level of a game engine programmer. And I might offer up a scripting language like Lua, which is a very popular scripting language, or in the Unity's case, C#. Make sense? Or I might turn to something like visual scripting. That's what Unreal does. Unreal handles it and says, we're going to create a visual scripting environment, as opposed to, allowing users only to write in lower level C++. Okay? And now Unity has Bolt. They just bought Bolt. And why? Because what we want to do is we want to make it more accessible for developers, other developers, other than game engine developers, and we want to make it so that we can protect the engine. That is the most important thing. We don't want the developer to break our build. That would be bad, right? So we give them just a script to write. If they write a script and it doesn't compute, we can output errors. That's no problem, but it's not going to break our build. Our engine is protected. And here's an example of that. I know it's an ugly picture, but it's an example of this idea of a chain of responsibility. So a good example is people who use C++, maybe that would be the engine programmer, right? They're going to have some core implementations. The gameplay programmer might be using C#, a higher level language, as an example. And they're going to be working on game systems, right? Some kind of gameplay. You might have a higher level guy, like a technical director or a designer. They might be using a scripting language like Lua, which is even higher level than C#. It's very Pythonic or Python-like, right? And they might be doing things like they might be working with a wrapper. And higher up, if you're a level designer or a scripter, you might use visual scripting or some kind of higher level editor where you drag and drop and save, right? So you can see that there's a need, or there might be a reason for having scripting APIs for as you go higher and higher up the hierarchy of responsibility. So why is this good, and why am I telling you about this? If you're a lead software engineer in your teams for GDW, and maybe in the future you're going to write your own little indie game, and you want to write it with, I don't know, OpenGL or Vulkan and C++, let's just say, right? Or you want to make your own scripting engine. You want to modify the Unreal engine and make your own game engine from the Unreal engine, which is possible because Unreal there's an open source version that you can download, whereas Unity is proprietary. And if you do that, if you make something that's very Unreal-like, maybe you're going to give it so that the opportunity for higher or coders who are not game engine developers to work with you and develop gameplay systems, but not break your build. And that's why I'm talking about it here. All right, guys, so that is the game engine architecture lecture. I think we've kind of touched about everything that you need to know this semester for game engine architecture. All right, at a very, very high level. I haven't really gone very deep. We are going to go deeper in some other lessons, especially when it comes to things like memory management and performance profiling. But over the next few lessons, and if we go back up to the top, one of the main things we're going to be starting talking about is this idea of object-oriented design. We're going to start thinking about different kinds of programming patterns, and we're going to start off with some simple ones. The two programming patterns you should know almost from the very beginning, and we're going to start off with these, is probably going to be the singleton pattern and the factory pattern. You can also learn about the command pattern. I think those are the big ones that you would learn about right at the beginning. Now, in the second half of the semester, we're going to go in more detail, but look for some patterns starting next week. All right, even though it's not listed here, I'm going to start talking about those design patterns that are required for your assignment number 1. Okay, any questions around the stuff we've talked about today? So we've talked about assignment 1, group assignment 1, we've talked about GDW requirements, and I've also talked about game engine architecture, and even gone into a little bit about Unity and how it's structured. Okay, guys, I'm going to stop recording now, and I'm going to take questions offline for the people who want to, come on the mic and ask questions about anything required from them over the next few weeks.